Can you speak in English, please?
Sorry.
Louder?
No sugar for you.
I try my best. So I would like to ask Sharad to introduce himself.
Well, when Linda asked me about myself, I said I'm the quintessential person that Judith always used to introduce, as this person needs no introduction.
No, that's crap. Everybody needs an introduction.
Yeah, except me. I'm the exception because I need no introduction. I've been here longer than Lou Ashwell. So I've been around for a long time. I did my PhD here at Wits and studying copper deposits. So this is my stomping ground. So I want to tell you about the geological setting and something about the crystals, the best carrolite crystals in the world that come from the Kamoya Sud 2 mine in Katanga in the Congo. So first of all, I have to introduce you to this mineral called carrolite, because it is not a very well-known sulfide mineral, except if you're in the Central African copper belt, where you'll find that this is the major cobalt-bearing primary sulfide mineral in the Central African copper belt. And this is, in fact, the most important cobalt-bearing mineral in the world, because most of the world's cobalt, about 80% of it, comes out of the Central African copper belt. And since this is the primary mineral in which the cobalt occurs, there are also secondary cobalt minerals, cobalt oxyhydroxides, called heterogenite. But carrolite is the main cobalt-bearing sulfide. It also has a little bit of nickel that substitutes for the cobalt, but the cobalt-to-nickel ratio is more like 10:1. So it's mainly a copper-cobalt sulfide. Now, this mineral, although not found in most other places, was originally discovered. Yes?
Can you go back 2 slides?
Lou Ashwell has got a question. Yes, Lou.
I want to know the scale of that picture of the mineral.
It's about the size of my fist.
And that one?
Okay. So let's go back to this mineral, carrolite. This talk that I'm giving you now, I originally presented last November at the Smithsonian Institution in Washington, D.C. And I had a very receptive audience there that consisted of the Mineral Society of the District of Columbia. And the reason is that this mineral carrolite was first discovered in a locality that is very close to Washington, D.C. It is, in fact, the closest type locality of any mineral to Washington, D.C. It's just on the sort of northeast west of D.C., and there is Carroll County, Maryland. Now, Carroll County, Maryland is what this mineral is originally named after, because it occurs in this mine called the Patapsco mine in Sykesville, and it was first described in 1852 by Leonard Faber, and this was this new mineral. Now, the Carroll County itself is named after this man, Charles Carroll, who has this name. He was a very wealthy Maryland planter, one of the wealthiest men, in fact, in the United States at the time. And he was one of the original signers of the American Declaration of Independence, and therefore is sometimes referred to as one of the founding fathers of the United States, although he was not involved in charting the Constitution. So anyways, if you like, carrolite is indirectly named after Charles Carroll. It's actually named after the county that was named after him. So before I go on to describing the crystals, I need to tell you about the geological setting of these crystals, and that is the Central African Copper Belt. So I'm going to introduce you first to the Central African Copper Belt, which is situated in Central Africa, in Zambia and Congo, in a big region of folded metasedimentary rocks known as the Katanga supergroup within the folded belt called the Lufilian Arc. And this was formed by a collision between two large cratons, the Congo craton, the Kalahari craton, in the Neoproterozoic. So the rocks that we're looking at are actually quite folded and deformed, and they form this large arc of folded rocks known as the Lufilian Arc. The Lufilian Arc gets its name from a river that runs down the middle called the Lufira River. Now this region is very well known as one of the major sediment-hosted copper districts in the world. The whole Lufilian origin has been divided into a whole number of different segments, but basically it is produced by collision of the two cratons that I mentioned earlier. And so if you look at a north-south cross-section through this orogenic belt, you see to the south there are intrusive granites in this Katanga High, and you've got a belt of folded synclinorian rocks. You've got an area where basement domes are outcropping, and then the external part is this external fold thrust belt, and this is the part where most of the sediment-hosted copper deposits are actually located. Now, in the Katanga region of the Katanga province of Democratic Republic of Congo, there are a lot of these deposits, and they are located in parts of the Katangan stratigraphy which have been quite disrupted during this deformation, and they occur as huge mega blocks of stratigraphy, which you can recognize here in this top diagram, and they have been dislocated during deformation, but also prior to that by salt tectonics. And there's been a lot of diagenetic fluid flow and brines moving through all of this lot. A lot of evaporites in this succession, which have been mobilized at various episodes, both before and during and after deformation. So it's got a very complicated history, and in addition to that, there is the supergene enrichment that took place afterwards due to weathering, and that has also produced its own set of complications. So if you zoom in on this region, this is the area on the border between Zambia and Congo. This little line that you see here is the border between Zambia to the south and Congo to the north. And you can see all of these mine symbols represent mines in the Zambian copper belt and the Katangan copper belt extending along an arc that goes on for about 450 kilometers. Also in the western part of Zambia, there's a whole bunch of mines here which are now referred to as the Western Copper Belt. And here the mineralization is different because it's not sediment hosted, but mainly in shear zones and associated with also basement rocks. And it's in vein type deposits here. But I'm going to concentrate on these sediment hosted deposits. And within this arc then, the rocks in the Katangan part are in fold thrust belts, which are allochthonous, whereas in Zambia they are still in contact with their basement. So you can see bits of the basement rocks here, which we have done a lot of work on in the past. So just to show you some of the stratigraphic sections through different deposits in Congo, going out to Kabwe in Zambia. And what we see is that the stratigraphy here of the Katanga supergroup, which are the host rocks, consists of siliciclastic rocks or red sediments of the so-called rat at the bottom, and there's a whole series of mainly carbonate rocks which are found in the facies that is mainly present in the Congo. And within these carbonate rocks, you see two major horizons that are mineralized with sediment-hosted copper mineralization consisting of copper and cobalt sulfides, and they are separated by stromatolitic dolomites in the middle. I'm not going to go into any of the details about the stratigraphy and so on. It's fairly complicated, but just to show you where the mineralization occurs in these two major horizons. Now, I'll take you to see some of the mines in the copper belt here. We're in the Kolwezi area. You see on the very western part of the Katangan copper belt, there's a whole series of open pit mines that are present here in this complicated region, and you can see a number of these open pits. They extend for about 10-15 kilometers along strike. There's a whole series of different open pits in here, and this is what these pits look like. This is the Dikuluwe open pit, which is quite oxidized. So they're basically mining oxidized ore in this area. In other areas, They'd be mining mixtures of oxidized and primary sulfide ore, and then in some of the underground mines, they'll be mining pure sulfide ore. So this is a view of the Mashamba open pit, and extending into the distance, just one pit leading into another. So this is in the central part of that Kolwezi area, the Visual, which consists of 3 open pits, etc. And you can see the coloration of the mineralization. Where it's darker, it's due to the presence of secondary minerals like malachite and so on, and also the cobalt secondary minerals. So here we see an old photograph that reveals the 2 ore bodies. I'm not going to go into the names, separated by this central region, which is consisting of stromatolitic dolomites. When you come close up to these so-called barren dolomites, which are not mined at that time, you see that they're full of chrysocolla, which is a copper silicate, and this is just kind of refractory, more silicate-rich ore. What they really like to mine there is malachite, of course. Kamoto is the only underground mine in that region, which was showing you the textures of the primary sulfides. Now, some of these pictures were taken a couple of decades ago. Some of these mines have closed since then. Kamoto had a big underground collapse a few years ago, and has been mainly closed for the past decade or so. So this is a cross-section through part of the Kamoto deposit, and it shows more or less flat-tipping beds, but they are part of one of these tectonically dismembered fragments of these Katangan stratigraphy. When you look underground, you can see beautiful stromatolitic reefs, like you see here, with beds onlapping onto these stromatolites, so it shows you it's a buried carbonate platform. And within these carbonates, you find copper sulfide mineralization. Here we see an example of a beautiful stromatolitic reef that was mined and taken outside of the mine offices in Kolwezi, and you can see that it was clearly a marine stromatolitic carbonate unit that's found there. The mineralization itself, you can see, consisting of disseminated sulfides. This is bornite and chalcocite. This finely disseminated rimming nodules of evaporites, like you see over here, and also disseminated and in veins. Now we come to another region here in the central part of the Katangan copper belt, the Tenke-Fungurume region, which has some of the largest unmined deposits in the world. This is an area with more than 1 billion tons of ore at 3% copper and 0.3% cobalt. And that's the equivalent of 6% copper, because cobalt prices are like 10 times the price of copper. So this is an incredibly richly mineralized region. And when you look at the outcrops of the Fungurume area, you see big parts of the stratigraphy like this. This is one of those big mega blocks. And you can see fairly intact stratigraphy in there. But you can notice that this area is completely devoid of vegetation or trees compared to the background. That is the normal vegetation. This is a mineralized block where there is so much vegetation that is actually poisonous to the plants. And so trees don't grow there. And so it forms a big vegetation anomaly that was found with aerial photographs in the old days, and you can see it very easily with Google Earth these days. So if you look at a close-up of these rocks in the foreground, you see that they are actually stromatolitic carbonates of the RSC. In that Fungurume area, we see rich outcrops that look like this, entire hills that are colored green from the copper staining of malachite. This would be running at quite a few percent copper, and some of the outcrop deposits could be running at about 10% copper in terms of grade. So they are incredibly rich deposits, and in the old days there were caves that were just made of malachite in which these things were found. So here is a close-up of that mineralized dolomite that contains the disseminated copper sulfides, bornite, chalcocite, and you see the same thing in outcrop, where the same textures are preserved, but the copper sulfides have been altered to malachite in this case. So that's what the sort of outcrop would look like of the Fungurume oxidized ore. And here is a fragment in the open pit of the mineralized rocks in contact with what is called the red rat breccia, which is unmineralized and which hosts these large mineralized fragments. And so, okay. So now coming to the deposit that I want to talk about, the Kamoya Sud 2 deposit in the Likasi district. This is a big open pit that was mined out in the 1970s, and it had an original size of about 10 million tons, 2.7% copper, 0.45% cobalt, very rich in cobalt. So this open pit has a big fragment of the Katangan Mines group, as well as overlying rocks of the Mwasha group that contains iron formations and cherty dolomites in the upper part. So this is a cross section that I got from the mine office. It shows a fragment of the mines group, which is actually upside down in terms of its normal stratigraphy. And this overturned fragment is sitting within breccias, and that is overlain by these normal iron formations of the Mwasha group overlying that. So you can see here in this image on the right, the mines group, and then the iron formation overlying that. And the overlying that are also these bedded carbonates with chert bands that we see here, which are in the upper part of that Katangan stratigraphy. So here we see chert lenses and nodules of diagenetic origin. You also see these jasperitic iron formations, which are really Neoporozoic iron formations related to the onset of the snowball earth, which would have followed immediately after this deposition of the Mwasha. There was a huge glaciation during which you had one of these snowball earth glaciations. So this is these rocks are very special in that they just precede that big snowball earth glaciation, and they have these stratiform iron formations. There's another one that contains magnetite and hematite as well, but they're really not so much part of our story. And then you see that diamictite of the Grand conglomerate that looks like this, the big glacial diamictite. So that was now the setting of this the Katangan, and for this particular deposit, the mines group fragment is the one that was actually mined in this open pit, and it had these the two mineralized horizons, the RSC and the SD, and these mineralized horizons were mined. They had oxidized ores that were full of malachite, but then they had, so the mineralization from that deposit, as you see in drill core, looked like this. It was basically laminated cherty dolomites with veins of, and also disseminations of, in this case, chalcopyrite and other sulfides, chalcocite, bornite, and you can see lots of veins cutting through this ore, and you can see also what looks like a stromatolitic dolomite over here. Now, in the open pit, you can see a spectacular outcrop of this overturned beds of these mineralized rocks. They are traversed by a series of dolomitic veins. These are all cross-cutting veins which were formed very late in the tectonic history of the Katangan, because they are totally undeformed. The veins are undeformed, although what they are cutting through are these rocks that have been overturned. And so these are very late veins in the tectonic history of the Katangan. And it is in these veins that we find very spectacular crystals of various sulfides, including the best crystals of carrolite in the world. Now, so you can see these veins, some of them are just a couple of centimeters, but they get to maybe tens of centimeters in size, in thickness, and they contain euhedral crystals of carrolite, which is this big silvery gray mineral, and also other sulfides, as I will show you. So here are some images. They are from various websites, and some of them are my own photographs. Lou Ashwell started this lecture by interrupting me about the size of the carrolite crystal.
Size is important.
Size is important, but not if you're a mineralogist. It is important, especially, but if you are into mineral photography, you will find, And Bruce Cancross is sitting here in the audience. He's our number one expert mineral photographer in the country. Intergrown with them are other sulfides, including very nice, beautiful chalcopyrite crystals, and this one has an inclusion of carrolite crystal in it. So a lot of these crystals are about 1 centimeter across, about the size of your fingernail, but some of them get to be the size of your fist. And they are cubic crystals, because carrolite crystallizes in the cubic system. It's part of the lineite group of minerals, and it occurs in the most spectacular forms. You can see in this case, for example, it's a mixture of cube and octahedron with all the different faces, and it shows very spectacular crystal forms. So these crystals came out originally in about the early 1990s. We had a meeting not in the 1990s, in the early 2000s. In 2003, we had a big meeting in Katanga. There was a big IGCP meeting, and this is when these first crystals started coming out, and they've been known since then at mineralogical fairs around the world, and you'll see them all over the internet. So aside from the spectacular carrolite crystals, you also see crystals of bornite. So here we see bornite, which is copper iron sulfide, together with carrolite crystals. And here we see some more. These ones that look greenish, have a greenish tinge to them. These are bornite crystals, and together with carrolite and some tiny chalcopyrite crystals as well, sitting in a dolomite matrix. So this is a crystal that's about maybe 7 centimeters across of chalcopyrite, very large chalcopyrite crystal with a big embedded carrolite crystal within it. And here we see the host rock, the dolomite. It's very, very clear. When I first saw these, I thought that this was actually Iceland spark calcite, but from our analysis, it turns out to be dolomite crystals, very clear. They contain about 30 ppm cobalt, and it was clearly precipitated from a cobalt-rich fluid, which also has produced the big sulfide crystals. And here we see some more of these carrolites. So let me show you these giant sulfides. Now these are big ones, but there are even bigger ones that are all in my collection, because I managed to get hold of them at the right time, at the right place. Here I am holding one of these in my hand, and you can see how big that crystal actually is. It's one of the largest crystals of carrolite in the world. This is in fact the specimen that we worked on, because we've just published something about it, and I'll tell you a little bit about that later. So this is there are very spectacular interpenetration octahedrons of carrolite, and very, very spectacular indeed. Here I have put a scale because I don't believe in that it will be. I don't care about the aesthetics, because I am a scientist. It is centimeters, I can tell you that. I don't use inches. I stopped using inches in the 1960s. So it's the sides of this octahedron are 7 centimeters long, and that is pretty spectacular. And I can confirm that this is the largest crystal, because I went to the Smithsonian and saw their puny collection of carrolite crystals from the same deposit, by the way. And they had just bought one that was a fake. And I spotted, it was not a fake crystal, it was a genuine crystal in a fake matrix. But what they do is, because the crystals are so hard, they put them in some kind of a concrete that's made up of rock fragments and whatnot, and then they break it, and then it breaks through the concrete, but the crystal remains, and then you have a crystal that's embedded in matrix. And the Smithsonian Institution had in their collections, and they had bought this from a major mineral dealer in France, a fake crystal, because I showed them what the real matrix is. It's these dolomite crystals, that's where they occur in the veins, and this thing was apparently in some kind of a conglomeratic breccia of some kind. And I pointed out to them that that's actually fake. Here is a very large chalcopyrite crystal. You can see the scale here again in centimeters. That's 7 centimeters. This crystal is about 10 centimeters big. It's one of the largest chalcopyrite crystals that's come out of Congo. It's also in my collection. It weighs about 0.5 kilogram. There's also what I think is probably the largest chalcocite crystal in the world. This is, again, because I've seen all the big collections in the world. I've been to the Smithsonian and the British Museum and the French museums and so on, and Vienna and Munich and Berlin. So none of them have got anything as big as this. So I have in my collection some of the largest crystals of these very well-known sulfides, and one not so well-known called carrolite. So I want to end by just telling you about some of the work that we've done recently. This paper came out a few weeks ago by Marta Sosnitska, who did her postdoc here at Wits, and she's now in Potsdam in Germany. And her study involved the supergene-enriched mineralizing fluids from the Mashitu South copper-cobalt deposit in the Katangan copper belt. But among the samples that she analyzed, she did some fluid inclusion work from these veins, from these other deposits, Mashitu. There are also results from the deposit at Kamoyasu 2. So the Kamoyasu 2 samples are these ones, these two. So this is a fluid inclusion, and you can see from PIXI analyses, proton-induced X-ray emission analyses, you can see the distribution of various elements, and that shows that there's even, there's chlorine, potassium, bromine, a bit of zinc also, manganese, strontium, etc. So her results show that the calcite, or rather the dolomite that hosts this, the big carrolite crystals, was deposited from a saline sodium, potassium, barium, strontium, chlorine-rich brine. And so this is what her conclusions are in this paper. The spectacularly large carrolite, chalcopyrite, borite, and chalcocite crystals from the metal-rich, formed from metal-rich brines. And from the chlorine to bromine ratios, we can tell that the brines originated from evaporation of seawater. And this was followed by infiltration of strontium and barium-rich fluids, which probably interacted with some of the evaporites in the succession. And that's what produced this spectacular mineralization. So, thank you very much. I want to end by waving goodbye. These are reflections in actual carrolite crystals. Thank you.
Thank you, Sharad.
Okay.
Is there any question?
Yeah, as long as it doesn't involve scale.